Welcome you all to the second session of Doctoral Colloquium. Yeah, we have with us Dr. Nisheeth Shrivastava from Google. So he would be talking on Google Maps, a planet-scale playground for computer scientists, giving you a brief bio of he works as a software engineer in the Google Maps team. He's leading a team of talented engineers to solve hard ML problems in the domain of NLP, user trust modeling, and abuse prevention. Prior to joining Google, he has worked as a research scientist at the Amazon Data Sciences team, a member of technical staff at Bell Labs. He earned his PhD in computer science from UCSB and BTech from IIT Kharagpur. He has 15 papers and patents in the areas of database, machine learning, and sensor network. He's interested in the areas of machine learning and data science. So welcome, Nisheeth. So this is going to be a talk from the industry for PhD students who are interested to move to industry after this. So yeah, thank you.
So hi everyone, I'm going to talk about Google Maps once. So I think the tone of this talk is going to be slightly different. I think I saw some very deep research topics and very nice presentation from Professor here. But so what I'm trying to do is talk about Google Maps, how we build it and so on. This is the work of like hundreds of researchers. So nowhere even like I wasn't involved in like 99% of them, but I'm trying to represent their work still. What I hope to achieve in this is give you a sense of like what kind of research happens in the industry, and hopefully sort of convince you that there is good research, although you don't see papers coming out of it because of whatever reasons and so on. But there is good research. There are areas where potentially smart people like you can sort of contribute to. And so yeah, with that, so what I'm going to do is I have maybe 25 minutes or so. I'll talk about how we build Google Maps, what are the research challenges, what are the kind of things that we work on, and leave the last few minutes for what I think are sort of good things to know when you move from academia or research to industry, which is a transition that I had to do a few years back. Okay, so Google Maps. So I think so. Maps has been there for like thousands of years. The leftmost map is the oldest map that we know of. This is from Great Babylonian civilization. From there, we moved on to paper maps, which are super useful. Now people have the same thing in their mobile phones on their pocket. Um, there is so while we have made good advances, we are nowhere close to done. There is Maps has a lot of potential, as like I think I may be preaching to the choir here, but Maps has a lot of potential which we haven't sort of explored yet, and we need a lot of research to sort of make that happen. I'll walk through some of these things, some applications, just to give a flavor of those. The way to understand Google Maps, or rather the technology uh, that is behind this, is in form of a layer cake. So we have sort of multiple layers of techniques which each build on top of each other, and augment each other to give the kind of experience that users get on Google Maps. So at the base layer, you obviously have your base maps, which is your roads and regions and geometry and those kind of things. On top of that, there are things like Street View, where you can see sort of photos of certain places, 3D places, and so on. On top of that, we have semantic information, which by that what I mean is things like businesses, your reviews and videos on top of businesses, and different information about like what is the operating hours and so on. So going from sort of the base, the bottommost layer, which is traditionally people think of maps, all the way to giving something that users can use. This is what sort of this layer cake does. Um, so in industry, at least, you always start from application backwards or user backwards. So I'll briefly talk through some applications that we are thinking, at least in Google Maps, and hopefully give you a sense of sort of what's coming in the future and what kind of things will require more effort. So just very quick. So obviously navigation, search. This is kind of what everybody does on maps, like go from point A to point B. Increasingly, people are asking for more and more variety of use cases and so on. So, for example, now so if you go to user surveys, right, people, the kind of things that they ask for is, okay, I'm sitting in IIT, triple IITB. can you tell me what is the vibe around this? Like, what are the cafes around this? What are the cool places to go? I have certain interests, like whatever, let's say Carnatic music, theater. Show me some theaters around this. So more and more from the simple use cases of point A to point B, route me and so on, it is becoming sort of much and more sort of more sophisticated use cases that we need to support. Uh, even in even in simple things like navigation, there are various interesting sort of new things that people are asking for. Like for example, I want to go from place A to B, but I want to do it in an eco-sustainable way. I want to take public transport. So tell me route that only has public transports, or I have an electronic vehicle or EV car and so on. So tell me a route that has EV charging stations around along the way and so on. Now, this is nowhere even close to the kind of use cases that we want to offer. But I wanted to start with this because I want to give you sort of a sense of there are new and new use cases that are coming, and this solving for these requires a lot of technology to be built in the backend. Like for example, EV charging station, we just don't have a sustainable way of even collecting where are all the EV charging stations, like government databases and so on. They're not complete and so on. So even solving for these kind of use cases will require significant technical challenges. I'll try to sort of motivate why map making is challenging, and I think maybe you guys may have most of the context here, but it's still sort of good to good for the audience to know. So I think the first thing is that users have a very, very high expectation of maps. They are much less sort of forgiving to maps versus other services. Like for example, even Google search, if you get the first 3 links and 5th one is important, well, sure, your requirements are met. But if you routed me through a wrong place, that is it. Like you'll see users complaining loudly about this and so on. So it's very, very important for us to get things correct. So that's the first thing. The second thing is maps, at least the real world, changes very frequently and in very hard, like unpredictable ways. And it's very hard to sort of, keep up to date to what is really happening in the real world. And I'll give you a couple of examples. Like COVID happened and we all were affected and so on. So with COVID, there were a few places which suddenly became super important, like vaccination centers and delivery, places who can deliver. Now, these weren't as important earlier. Now, suddenly everybody wanted to search for vaccination centers, and your coverage on vaccines, it's just like, and we had to build all of these things in a few months just to make sure that, we are getting to what people are searching for. Similarly, if a road accident happens, or let's say a flood happens, people want to be routed in different ways, right? I don't want to go through this because there is, this road is flooded. And now this is something you need to understand in hours, if not minutes, and make sure that that map is up to date. So ever changing, fast, it makes it very hard for you to sort of keep maps up to date. Now, a few techniques. These are sort of, we deploy many different types of data sources, type of techniques. Some of these are listed here. I won't go through all of them. The point is that there are pros and cons of all of these. Like web extraction has certain good things you can get in scale, but it will be old. It won't be very fresh and so on, and you don't know how much you trust that information. So all of these have pros and cons. They together, we believe, complement each other and give us sort of good sort of complementary data sources so that we can build enough coverage on the kind of things that we want to do. What I'm going to do is talk about the bottom two, which I've put in bold: crowdsourcing and imagery. And I think, because I thought this will be sort of most pertinent to this particular crowd. Okay, so moving to crowdsourcing, what people don't realize is a large portion of map is actually built by other users of maps. We have, some 1 billion plus monthly active users. They actually give us every month hundreds of millions of edits on maps. And these are the kind of edits. So they help us sort of, change and add roads. So if some roads are not there, people come and add those. They add new businesses, they change businesses, like if the phone number has changed or the operating hours has changed and so on. They obviously give us, things like reviews and photos on maps. And they also give us very interesting attributes which are very hard to collect otherwise. So like, for example, one example is on the right where, you ask, is there a parking structure? Now, it's very, very hard to go to web extraction or any other place and say, is there sort of a parking near this place? Or does it serve good coffee, or is it kid friendly? These are inherently things that humans know, and humans actually tell us this kind of information a lot. Now, the challenge that we have is, so we get all of this information, you have to take that, process it, make sure that all of your layered cake and so on are consistent and updated within minutes, and do it as fast as possible. Now, so just coming to crowdsourcing, users give us a lot of accurate information. Sometimes they don't. And siphoning out which one is correct and which one is not is a very hard problem. I'll try to cover that in the next slide. But users do give us incorrect data, sometimes because they just make mistakes, like either they're confused by our user interface, or they just think that they're giving us the right information, but they themselves are wrong. They also do it for various malicious reasons, like if I may have something bad to say about a politician, and I'll go and say it on the map because so many people look at maps. People also do it for fraud reasons, like I may want to, I put fake businesses just to siphon off, business and make money myself and so on. So there are various reasons why we get incorrect data as well. Now, so far we have been, or rather not so far, like maybe a decade back, all of this used to be processed by humans. Like we'll have this, giant set of operators who will sit down and look at everything and say, oh, is this road correct or not? Is this place correct or not? And obviously that can't scale. And over time, we have moved to machine learning models. We try to classify both the content that we're getting, like if you're giving me like a name, does it look like a genuine name? If you give me a photo, is there some bad thing in the photo and so on? And also to score users, where we know a lot of user history on what they have been doing and so on. So we build user classifiers and say, how much do I trust the user? Hence, how much do I trust the content that they're putting? And then does it stitch together with other things on the map? Like you have to again like think of that layer cake and see if things are consistent. Like if you're putting a business on the middle of the lake, well, most likely it doesn't exist. So we believe multiple different types of technologies to sort of solve this problem. I think the first one is, I mean, just like everybody else, we use ML and now LLMs and so on. BARD, not GPT, because we are at Google. But so machine learning is core of what we are doing. There is a lot of techniques, both in language processing. Okay, sorry, there was a confusion at the time. So both in like language processing, like text and so on, also images. We have user understanding models, like I said. We also try to put humans in the loop. So there are many cases where an algorithm may have drawn, let's say, a road, or decided that the space exists, and sometimes users are good sources to verify that information. So we try to make use of crowdsource as much as possible. Try to go ask users, do you believe that this change that we are making, is that correct or not? So I think so with these techniques, and all of these requires machine learning in some form, like user understanding many times requires graph models to sort of connect multiple users, try to see if their patterns are similar and so on. So this is sort of the first area that I wanted to cover, which is sort of how we use sort of crowdsourcing in users. The second one, which may be more interesting because I've heard similar things in this colloquium, is on imagery. So the different types of imagery that we collect. The first one is street view. I think you may have seen this. This is basically, if you go to maps, you can point, there's some funny cartoon on the map, you can point it to a place and it will show you a 3D panorama around where you're standing, and you can try to see what that place looks like if you're really actually standing there. And the street view is collected through various different sources, mostly by the street view cars which are running around in different places. There are also interesting, sort of hard to get places where cars can go to, but we have very interesting ways of collecting data from there. For example, there's like lakes where people are actually canoeing and with like a 3D camera on their head and trying to collect data from there. Um, Now, if you look at Street View, though, it's not just a bunch of images. So you can actually extract a lot of semantic information from that, and that's exactly what we do. For example, there's some examples are shown here. Like you can know where there is a traffic light and so on. You can detect street signs and so on. You can detect um, speed limits. Like if I want to show that this road has whatever only 25 kilometers per hour, now that is there captured in some Street View data. You can also get addresses like street numbers, street names. You can also get businesses out of that. If somebody, let's say, adds, like going back to crowdsourcing, if somebody adds a cafe at some place and you can verify that in a Street View image, then that's a very strong indicator that, yeah, this actually exists and nothing is wrong. So we do use a lot of pixel models to extract this kind of information. And obviously, again, we have to overlay this with the geospatial data and make sure that, okay, yeah, there is a street number here, but it's not pointing in this direction, but that direction. So you have to also do this with the correct geolocation. The second type of imagery is overhead satellite imagery. So this is, like, you guys are aware of this, obviously. This is sort of fundamental key data that we get to drawing roads. So today, if you look at most countries, especially in developing countries, there is no single database where you can go to and say, oh, in this small village, tell me all the roads that exist. Right? There is this, it doesn't exist. And this overhead imagery gives us sort of a lot of data to actually build this. Now, like you can imagine, I think you are the experts here. There is like extracting like looking at imagery and then extracting roads from it is pretty challenging. We do deploy many pixel models. We also use the existing data that we have. Like if I'm drawing a road and it doesn't connect to any other road, well, most likely it's wrong, right? Um, so I think so there is so we try to extract both segments and intersections where you say, okay, if there is like multiple roads going out, there must be intersection. How do you model that and so on? And also connect it back to the rest of the road so that you can actually route to all of these small villages, in the right way. This is just an example of what you can get to with this very powerful technology. Like earlier, just the gray area, there's nothing else. That 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 red point just represents like maybe center of the village or something, and from there you're able to draw all of these roads and so on. So again, very useful technology. Coming back to what technology sort of makes it actually take. So again, like you can imagine, we use a lot of machine learning here. Pixel models are sort of the core technology that builds it, but it's not just sort of pixel models. We also have sort of very strongly labeled data set, and that's something that with humans we try to keep on updating, because getting to sort of for example, there's so many things that we want to model. Like you want to model, okay, what is the width of the road? Now, looking at, like, there is just no such data set that exists, and we have humans who actually can label this, but making use of that is also critical. Compute power, like at Google, that's one good thing that we get. Like we have so much compute power. You can actually process these like hundreds of millions of images you get every day, and turn that into something which is usable and so on. And yeah, advances in deep learning and so on is sort of powering this. And so I will, I'll just quickly talk through a couple of challenges that we see in this area. The first one is sort of just the diversity of things. So when we extract speed limits and road signs, right, we don't want to do it for one country like US or India. We want to do it globally. And there are like so many languages, hundreds of countries, each having different road signs, each having different representation. Like, for example, stop sign actually means yield in many countries, which is just like very hard for you to get a consistent model on. So diversity is one, churn is the other one. Like I talked about this earlier, like even things like simple things like roads, right? They actually change very frequently in the real world. Like there used to be a traffic sign, a traffic meter here where you're supposed to stop. The government has removed it. Now, if you sit on that and you don't update it for months, you'll completely miss this kind of updates for months and months. So I think again, catching up to real world churn is another challenge. The third thing is just edge cases. There's like so many crazy edge cases that happen. Like there are like forests, or rather like forest areas where majority of like a stop sign, I don't know if you can even see the stop sign there. It's actually hidden by very nice grass. So when you look at that and say beautiful, and my models look at this and say, oh my God. So I think so handling corner cases is going to happen. This is, yeah, I mean, with so many users, you're going to hit into this. I think I have 5 minutes, 2 minutes, 5 minutes. Okay, awesome. I'm going to skip over all of these nice things and talk a little bit about PhD to industry research. Now, so I was thinking about so my background, I did my PhD. I was working in a research lab, so I was sort of, and then I transitioned to industry. So I did go through this transition, as maybe some of you will. And I was thinking back on what would help me, or what are the learnings that I have from that transition. And some of these I've tried to sort of capture it in a few bullet points. I think the first one is you're getting amazing experience in terms of defining a research problem, solving it, and sort of doing it with sort of at with rigor. Like you don't just make a solution, you make a solution which, like, you publish papers and so on, that others criticize it. You try to make it really solid. So that is the first thing. You are solving deep research problem. Do continue doing that. Do not leave this whenever you sort of move to industry, if you do. The second thing, and this is something that I learned after I came to Google, which is you have to build for scale. Like POCs, like at least in like large companies and will you have like hundreds of millions of users, POCs just do not scale. You will build this, and then as soon as you launch this, you're going to retract it and then build it again. So do keep this in mind. It's thinking about this from day one actually helps a lot. So build for scale when you're doing. The third one, I don't know. I think this is probably the most important one, which is focus on impact, focus on product impact. So if I look at my work, I solve user problems. So there's a product. I'm going to sort of improve that product, and unless I can deliver impact on that, I'll get technical satisfaction, like sort of that I solved a great algorithm, I came up with something. But unless it makes an impact, I mean, trust me, like focusing on impact both will help you grow, and also it will give you much more satisfaction than like writing a paper. I've done both, so I can sort of tell the experience. Um, User centric. I think sometimes, like, think backwards from your users. What are the kind of use cases that they want to see, right? And if you are enabling that, like if you're solving anything for a real user, it is going to be important. And then I'm sure that all the technical knowledge and so on, you will apply to do it scalably and in the right way. But do think backwards from users. The last one is adopt. Technologies change. I did my PhD in algorithms, databases. I'm now completely working in machine learning. You have to go through these transitions at least like once a decade is sort of my best guess. So be ready to adopt. You will get, you are getting good, you have good skill set, you're smart, you'll get good problems to solve. They won't be in the domain where you are working today. You will have to move and adopt. So be ready to do this. And that's it. Yeah, Shweel. I'll stop here and see if you have any questions and so on. But how do you tackle scenarios like that we have accidents where on the road and then people want to recommend that particular vehicle, then who manages this and back end? Right. Okay. So right. So the question is that we try to reduce human intervention as much as possible because ML models are faster. But how do we capture things like accidents or road closures which happen in real time and so on? So the simple answer is that there is no ML algorithm that can magically detect this, right? So we are relying on humans to actually to give us this information. So we don't try to cut off humans out of the loop. What we try to do is, if let's say a consumer of maps and so on is giving you that data, how can you make it on maps fast? Now, if that step requires us to have some human looking at it manually and verifying, and then it becomes very slow. But if you have ML models and sort of automated system that can take that user data and then process it fast and update maps, then that's fast. The signal which is is coming from users. There are other ways we get this signal. Like sometimes you actually get you see sort of speed of vehicles and you say, oh, suddenly everybody is stopped here, right? But generally, like humans are very important for these kind of cases because it's just very hard. It's very hard to get any other signal and data source for this kind of a problem. So there is no single answer. I mean, it depends on what kind of place and so on. Like for example, in dense areas, we generally do it much more frequently because actually businesses change there very frequently. So every month you'll see like 10% of businesses will just like disappear and new ones will come. Whereas in smaller places, I mean, it's basically a resource question. Like you have only so much resource, and what is the right places where you will see changes. And so yeah, I think yeah.
That they never disclose the privacy and segregated techniques or approaches which they are using. So can you please highlight on this, what kind of things they are doing and how it is making them so protected that the vandalism and all you have mentioned. So
Right.
even though people are trying to do, they are not actually being successful in that.
Right. I don't know if I'm supposed to talk about that, but so jokes aside, I mean, see, so you talked about a few different things, and so there's security and privacy and so on. There is also like removing abuse, whatever type of abuse from maps. So overall, like Google takes it very seriously. Like for example, privacy and so on. Like we take it very seriously. Like it's not like researchers have access to all the user data that you have uploaded. No, we have to go through like for every small thing we have to justify why do we need access. So I think privacy in that sense is sort of very seriously taken. Similarly, like so abuse. I think there are so there is a large team. I'm part of that team which takes care of these kind of things like vandalism and so on. And we have made a lot of progress in terms of like stopping these things. Like earlier, it used to be much more easier. Now we can actually catch these things and take them down very fast. Our techniques are not perfect. We are still sort of working on improving them. And so that's why I said like there is a lot of like technology innovation that we need to do today. Like we have seen people are also innovative when they try to vandalize map or abuse anything actually, right? So for example, we see weird cases like people just putting I mean I don't so I want to make a political statement, I'll put it on maps and they'll do it in such amazing ways across sort of different edits that it will even humans find it very hard to catch. So we are working on it. I don't know how much more I can tell, sorry.
We can just take two comments, one question. I think Raj mentioned that Gemini is coming. It will be really on 17th of December. I'm really looking forward to it. Just one other comment. I was in China just a few weeks ago, and China doesn't work at all. So I was in a taxi and I was looking at the map that is developed by Chinese. And so it said it was very advanced. And much more interactive. So it should integrate everything. So, for example, Uber is part of map. If you know what you call a cab, just cab. Not only that, just one more example. So if you're sitting at a traffic light, the traffic light is honking, whatever second left, it means stay. So they are really far.
Yeah, that's yeah.
Just one question about the legal aspect of crowdsourcing. That if something is there, is not generated, but provided through the provided platform.
Mhm.
It's not right or that's how do you get
So I think so it depends on the kind of information. Like for example, if somebody puts a photo and let's say it's a bad photo, so we have the same legal requirement as any other third party platform. Like for example, uploading photos on Facebook, you have the same thing. If it's a bad photo, then Facebook should take it down. Similarly, Google should take it down. Now, in terms of sort of so incorrect data is something which which is sort of hard to sort of put, like for example, if we knew that a road is wrong and we purposefully let it there, then that's obviously wrong. Like, but in many cases, like if a user came and drew the road and our model said, yeah, this looks okay, and that road was wrong, that is a slightly challenging thing, because we don't have any other data to sort of substantiate them. And so I think that's where like I don't know what are the legal ramifications of this, but I mean, this does come with these kind of challenges, and we are sort of, I mean, so legal is sort of a very strong sort of, word, right? There is also user consequences that we have. Like if consumers find this to be bad a lot of times, then there are like other implications. So we do take it very seriously. I don't know if that answers your question.
Thank you, Dr. Nisheeth, for the wonderful and insightful session. So moving ahead, now we'll have the next presentation by Anindita. And it is on study of urbanization, environment, and sustainability. So one more time, I will repeat the guidelines. You need to you need to finish the presentation within 15 minutes and 5 minutes for question and answer. Before 5 minutes, the tag will be shown to you. So quickly try to wind up your session so that we can go to the next session in time.
Good afternoon, everyone. So I am pursuing my PhD in IIIT under data science, and my guide is Professor Uttam Kumar, sir. This is my topic, which I'm presenting: urbanization, environment, and sustainability. My flow of the talk: first, the introduction, then the problem statement, what I've studied, the objectives of it, and I'll show the results along with my study, and finally the references. It's the study of urbanization, and all of us know how the rural areas are transforming into urban areas. And of course, the statistics are changing. Now in India, it's said that 69% population is rural, but actually these figures are changing rapidly. So the urbanization which is happening in India is actually unplanned and haphazard, and it is projected that by 2030, about 600 million people will stay in urban areas. So these transformations are happening at a fast pace. So how are these transformations affecting the environment is a topic of study which I'll be presenting today. So if I say in a world level, 13% of global population used to live in urban areas in 1900, which is today more than 50%. It's happening rapidly. And what are the problems, environmental problems we are encountering as a result of that? So urban island, of course, the core of the city, sometimes more heated up because of the concrete and high urban density. Pollutions are more. There are large waste generation, inefficient consumption of energy and materials. If there are urban sprawls where people are staying at a distance and traveling every day, and they will lead to more and more fuel consumption, more energy consumption, which is actually inefficient. So I'll be presenting about Bangalore, which is my study area. So it was the city of lake, and it had a very favorable climate, and people migrated to Bangalore. Because of that, there were establishment of new industries, textiles, and in start in 1990s, IT industry. So a lot of migration happened, and a lot of built up also happened, which was quite unplanned in that way. And 300% was the increase in the peripheral area of Bangalore, which I'll show you later in the maps, where it was completely unplanned. The core areas of the city had greenery, and even the land surface temperature wasn't much affected in the core than in periphery, which is the result of the study which I'll be coming to. So it impacted the temperature and it wasn't accounted for. So here, which I've studied, is urban growth pattern. So this is keeping the BBMP boundary. If you see, this is the boundary, and we see the built-up area, which is in red, how it has been increasing, and it has reached a saturation point. So there is no space left for to build in the same area, and also the boundary of Bangalore has changed and it has been increased. But we had taken a buffer area more than that, and to see in which direction the city is changing. So this is the buffer area to see the direction of the roads, how the city is growing in particular roads, and how the patches of urban areas are also increasing. So here, when we see the BBMP boundary, one of it is the BBMP boundary, which is, you can see below how the built-up has increased, and the other one above is the with buffer area. Here, the others are fallow land or other barren lands which are included. But even in this above map, you can see the increase in the built-up area here. Actually, I forgot to mention that it was done by machine learning algorithm, these training sets by using random forest. So I'll come to another study. It was regarding these seasonal variations of temperature. Does urban heat island varies according to the seasons, or it's the same? So we had used Landsat 8 OLI data. So in that, band 10 was used, and here April was used, sorry, March and November were used. We used different months for our study to see how the correlation happened between temperature, NDVI, normalized difference vegetation index, NDVI, normalized difference built up index. So in case of summer in March, what we see is that higher correlation between built up and LST. While when we come to November in winters, it is 0.28. We had taken some random points to see the correlations, and it was 0.28. So the conclusion of the study was the urban heat island effect is more in summer than in winter, where the concrete gets more heated up. So when we say about urban temperature or concrete in summer season, the impact is more than in any winter season or any other seasons which we get the data from. So this is the method which I have applied. So we had earlier extracted the built up vegetation, water, and others, when we also have seen how the temperature varied across these classes. So LST of built up was, when I say the average, 36.18 in March, while in November it was 22.40. So of course, what I said about the urban heat island effect, it varied across the classes in which the study was conducted. When I see the even the distribution we see in March or summer season, the NDVI or LST or NDVI or LST, which was seeing, the aggregation is more, there's less variations. But when we see in November, the spread is more in the data between NDVI and LST. It shows more lumped and clumped relation, and here there are more variations which we can see in the below graphs. So now I'll come to urban thermal field variation index. So this was done to find out the thermal comfort in these in Bangalore, and here I have taken a ward level study to understand that. So here Bangalore was divided into 6 categories to understand which has more ecological comfort than the other categories. So the method which I had used in the study was it's given here, and here I had, along with that, I had also done a spatial autocorrelation study. In that, we in order to see, I have done a spatial regression taking LST as a dependent and other NDBI, NDVI, and other categories as a independent values. So here, because I've done the spatial regression, I had to find out the spatial autocorrelation of the land surface temperature between the wards. So here, the spatial or the Morris value of LST was 0.63. Here, if you see, it is a positive spatial autocorrelation. This is an example to see if it is negative, it will be not clumped and it will be highly sparsely distributed. Extreme positive is a different phenomenon, but here the temperature in wards with higher temperature were clumped together, and the periphery area, which was little different temperature, were clumped together. So because it had shown a little higher positive spatial autocorrelation, we could do the regression study, and it was 0.89, the R square value between LST and other variables which I had studied for. I'd taken vegetation index, built up index, then elevation and other factors which are can be actually related to temperature in the study. So here, as I said, I have done the ecological evaluation categorizing into 6 zones, and this is the ward level map of Bangalore. This is BBMP boundary, and the updated one hasn't come up. With this boundary, I'm working on the ward level study of Bangalore. So even if because I said that in the middle, it was planned for and it has greenery. If you see in the map also, you see little temperature changes, more smoother temperature here in the middle of the city core areas, while when you go to the periphery, you see higher temperatures, which was told before as case of unplanned urbanization. So of course, here also we are getting the same, like more smoother or comfortable temperature here than in the peripheral area. Actually, in order to correlate that with humidity, the data set of humidity is available at much low resolution of 10 kilometers. So such kind of comparison in ward level cannot be possible with temperature and humidity with the present data set availability. So comparison can be done with cities to see, even when I say about thermal comfort, if humidity also says the same thing. So urban sprawl pattern has been used to see how the growth has taken place in Bangalore. So here I have taken 2014 and this is 2021 data set to see the built up, how it has increased. So when I used urban sprawl pattern or spatial matrix here, which is to quantify urban sprawl, when I say take patch density, how the patches have increased over the years. If you see 2014, you can see the roads very clearly in the supervised classification image. So here in 2021, you see how the patches has increased along with the roads, how the growth has taken place. So with the help of the matrix, the growth is being captured along with the roads and along with how the urban sprawl has impacted Bangalore and how the city is expanding in all the directions which we are seeing using a buffer from the boundary. So even I used some multiple ring buffers here to see if the temperature changes as we go further from the core of the city. So here, when we see in this map, from the center, it was 29.25 or some values. When we go up, this is the mean. It's 32.9 or so. So even the temperature is going up as we go from the center of the city towards the periphery to see how the growth of the city has increased the temperature and how the greenery is also declining throughout, which is not evenly distributed. So before that, a study was conducted, phase 1, 2, and 3, where to study the pandemic. Here, in pandemic, we see a lot of temperature changes which happened between in 2021 and 22. When we compare the temperature in phase 1 from 2000, when you see the phase, if in purple color you can see the 2021. Here, if you see in this is summer and this is winter. The summer temperature is between less than 35, while 2014 and 7 you see the most of the temperature are in the range 35 to 38. So we see also in the temperature map how the percentage of area varied in 2021 because of the effect of pandemic. There was more we see that more of the environment changed and the temperature was also smoother than other areas which I had examined. I'll come to the maps also, which to show. So this is the pollutants map because I wanted to identify the zones along with the pollutants and I wanted to see how because of the less emission, how the land surface temperature also changes or varies. So I'll just come to the map quickly. So here, when I see in the pandemic, which you see nitrogen dioxide in figure C and D and C and D, which we see this is C is Delhi, and this is Bangalore. So here in Delhi, I'm just seeing because of the pollution level, the other cities also, the correlation is less between pollutant and LST, while you see in 2022, after that, the correlation index is more. So after the lockdown, when economy opened up, of course, the correlation is also more. Here, when I see the correlation between LST and nitrogen dioxide, which is a greenhouse gases, we see more interaction between the pollutant and LST, and we see it's going higher up. It starts from 0.57. Even in Delhi, it starts from 0.70, the correlation index between nitrogen dioxide and LST. So these are actually, there's a relationship between these two components. This is the land surface temperature of Bangalore. If we specifically look at summer, also we see the changes, how it was in 2019, how it was in 2012. So the changes which I had shown in the graph can be depicted here. So I'll come to, these are the problems, and I'll come to the urban green spaces, the mitigation effects, how it should be there, how it can be mitigated. So here we can see the ward level distribution of green space also. What is the total green space? And we can categorize the green spaces into low, moderate, high, and very high. So I'll just come to the slides where this is LAI leaf area index, where there was 100 to 100 grid was overlaid on the study area to see what is the percentage of green space, which is the low quality green, high quality green, moderate, high quality, and very high quality green. So here we see in the middle center of the region, we see high quality green, and which is available, and also accounts for the temperature changes, which we saw that it was temperatures were quite smoother in the area, central area, than in the peripheral area, which we looked at. So this is the green index map of Bangalore. So there are some wards which were identified, which had more temperature than the other, which is given here. And when we say that there has been land use change, economic activity, energy use, and land transformation, which is happening, which is the mitigation which we can give is, of course, new spaces and green spaces, which are actually helps in mitigating the urban heat island effect. And what is the importance of this to the surrounding area and the well-being of the residents of the particular ward level. So we are seeing the urban green spaces, various parks, their area, and how the temperature are changing as we go away or near to the parks, and what are the impact of this park which are present in various ward level. So this study I'm conducting right now. So these are the references, but I wanted to show you even in other cities also during over. So thank you. Yes, yes. I have a lot of conferences, and I've just drafted it to send to the turn. InGARSS 2021 also I presented the impervious surfaces connection with LST. Then in one of the pollutant is accepted in MyGrass, which is happening. Then there are several conferences. I didn't mention that there are a lot of conferences which it has been already published. Conference it's published in proceedings, and 2 or 3 are drafted to be sent. So I haven't mentioned that. Landset. Yes. Yeah. 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 I've used Sentinel P5 also, that is pollutant laser. Yeah. Landsat. Yeah. Yeah, that was LAI for April 1 month. But what I'm doing is urban green spaces. I'm taking which are more than 10 hectares. What are the urban green spaces which are less between that? I'm categorizing according to sizes and seeing the impact, like how they're mitigating and what is the NDVI associated with it. That helps to mitigate. If I'm showing some problem, what is the way to mitigate through urban green spaces, and which are the place which doesn't have ample amount which can be actually told the locations to find out, or urban planners to find out how the city is growing, even in sprawls also, how it is growing along with the roads, or is there any urban green space, or even if I'm saying small and it is not identifying if the basic amenities in those places which are located can be provided. So it's even in patch analysis, we say it's that growing along with the roads where the number of patches are more.
That makes sense.
Yeah.
Then, see, anytime that good, right? Some samples, standardized samples, right? That mostly density of
Criteria is technologically assisted decision making for sustainable urban development and urban practice. Namaskar everyone, a very good afternoon. So today I am here to present my work on can we hide? Okay, no problem. How technology can assist in decision making. I am Jayati Vijayvargiya from Indian Institute of Space Science and Technology, Ramya ma'am's student. So today we all know that more than 57% of the population live in urban areas. Okay. Thus, understanding urban scenes become very crucial to take informed decision making, sustainable city development, and effective urban governance. Unlike before, today the urban fabric is not only changing in its shape, but also in its structure and size. Shape, structure, and size. And when I talk about urban fabric, a lot of features, for example, street patterns, the vegetation pattern, the land use zoning, building design, a lot of figures come into the picture. This rapid urbanization is leading to redevelopment, which is leading to gentrification, which is improper urbanization I can make. And as a consequence, typically in Bangalore and Hyderabad cities, we can see urban flooding, environment degradation, and ineffective policy implementation happening. Thus, role of decision making becomes very, very crucial. According to the United Nations SDG 11, the sustainable cities and communities, it has laid out the three main parameters for policy making. That is, it should be resilient and sustainable. It should involve community engagement, and it should have monitoring and reporting of the development, whatever is happening. Regarding this today, as a technical person, the need of the time is to bring out or involve technology in answering these three pillars of SDG. When I talk about resilience and sustainability, our technical assistance should also accommodate the physical urban expansion, whatever is happening, and it should be adaptable and flexible. The community engagement, the product, whatever we are delivering, should encourage the environment sustainability and also provide the simulations of development if happening. And at the same time, it should help in effective policy implementation and centralized governance. Today, airborne LiDAR data, which provides us with precise 3D point cloud data, is being utilized in a lot of applications like 3D city modeling, transportation planning, etc. And we can see that its utilization in by virtual engagements such as digital twin and metaverse. But the need of the time or the potential, the data, not only the LiDAR data, but other data is happening, is in a lot of other applications like mapping, planning, estimating, smart governance, etc. So my work is to look to the potential of airborne LiDAR scanning beyond its normal use in DM calculation and classification and mapping towards decision making by providing statistical and analytical insights. But implementing these insights or getting these insights from ALS point cloud data becomes very, very challenging because it is very unstructured. There is a lack of semantic context. There are operational and computational limitations that a stakeholder has. And also at the same time, when we try to convert data from one form to another, there is an information loss. Thus, in this time, like we have the opportunity, how we can use the existing technology, that is airborne LiDAR scanning, to expand its utility horizon with the existing technology and with the existing need of the time together, so that we provide a framework that can be helpful for multitude applications pertaining to sustainable urban development. So, so far, as I told you, related works, the data has been used for mapping, mainly by machine learning and deep learning, for visualization by various tools such as cesium and pottery we are having, and also for one-by-one applications like urban solar potential calculation, flood risk monitoring, vegetation analysis, for mangroves and urban, like some people talked about urban greens. But how we can convert this data to information? So when we potentially see this LiDAR data is formed as a file-based format, in which we are having the point cloud information, X, Y, Z, some semantics, for example, RGB intensity, and the class related to it. When we try to even convert this data and use it in as PostgreSQL from the relevant works in the literature provided, they are just converting this point cloud data, making clusters and extracting some insights from it, which are not very semantic insights. So the question comes like how we can use this data, add value to it, reduce the search space, extract the relevant information, and use it for the practical applications as per the need of the time. So here I propose the analysis ready point cloud, which is a framework in which we can utilize large scale point cloud data. A lot of researches are conducted on a very small scale study, like 1 road, 2 road, or maybe a very limited area. So this is a framework for large scale utilization, because the applicability is for city scale. When a decision maker is seeing, he will not be seeing how it is performing on a road or two, but on the city at large. Then how we can embed the parameter of scalability and sustainability. Cities are expanding, this parameter of scalability is very efficient if I want to make this framework sustainable over a period of time. And also by semantic enrichment and reducing the search space if I search for any information from that data. So in this work, what we are trying to do is convert the airborne LiDAR point cloud data to analysis point cloud data. And to convert the same, we have to get in the 4 strong pillars, as I mentioned. The knowledge base creation, knowledge embedding, knowledge extraction, and visualization. So the first step that comes is knowledge base creation. A lot of work has been going on in this field. Machine learning based approaches, object based or point based, on handcrafted features or deep learning based features, or deep learning based point cloud semantic segmentation are also in picture. In this work, we have done feature based machine learning, PointNet++ and RenLaNet. We are still on to making progression in that. So for the knowledge based creation, because it is for classification, we are using 2 benchmark data set. This is Wengen 3D data set, and this is Dale's LiDAR point cloud data set, and this is our Trivandrum data set. Here I would like to bring your attention to the perspective LDQ. LDQ is land diversity coefficient. That is a complexity index that we have proposed again. When we see the Western world, this is a house. After that, there's a space, there's a tree, and after a space, there's a road. But in the Indian context, this is the house. On top of that is tree, below that is tree, and the road is going just near the house. The complexity is very much. So we have diverse this land diversity equation. That is with respect to each point in the point cloud, like out of n neighbors, how many neighbors are from different classes. And that is where we have used these 3 data sets. This is a small data set, but with a good LDQ. And this is a large benchmark data set because our study is on large data set. It is 10 square kilometer. And this is our Trivandrum aerial LiDAR data set that we have named as a TAL data set, which we have acquired for our study. The other pillars, as I mentioned, comes about knowledge, embedding, information extraction, and visualization. For this, we have proposed that how this labeled point cloud data, we have to metaphorize it to ARPC, application ready point cloud, which can be used for a lot of applications. And here now I am going to tell like how we did that. For this study, we used the Dales and TAL data set. As I mentioned, Dales is a very large data set of 10 square kilometer having a point density of 50 points per meter square, and we acquired the random aerial LiDAR data set over 9 square kilometer. We have labeled it having a point density of approximately 12 ppm. Now the concept of this is a urban landscape can be conceptualized as a collection of urban objects. Okay, so we need to transform this point cloud first to collection of urban objects as a first step. And here the objects can be of different types. When you see the scenario of Vehingen as shown in the picture, we are able to extract individual trees very easily by visually perspecting also. But in case of Trivandrum, we are not able to do that. So in this case, I have created two different things, like from the aerial LiDAR data set, we are extracting either individual object or a semantic segment. If we are able to extract individual house, it's an individual house. But when I talk about vegetation, especially high vegetations, either it is a vegetation patch or an individual tree, and with different parameters. If it is a tree, or what is the the diameter of the tree, and canopy and other things. Similarly, the shrub patch, the ground patch, and the grass are also being extracted. After we have extracted the individual objects, we come to representing individual object. As I told, collection of object. Now we have extracted object. Now we are representing it. Representing it with some kind of characteristics. So here we are extracting the geometrical attributes, shape, size, height. It's like other parameters. For example, in case of Trivandrum, we have the word data. That word information, semantic information also comes into the picture. Then for storing, we are using a bimodular storage framework in which we are having a database. And with the database, we are linking the 3D point cloud data. So in the last format, we have seen that we have XYZ and class information. In our framework, we are having XYZ and unique ID of the object to which that point belongs. So if I have to now, then we have a query framework, which is based on the metadata-driven query approach. So if I want to query, I can query from the database. And the output that I will be getting is a point cloud information that I'm getting from the point cloud. So we have semantically enriched for it. Then we have used various visualization tools to finally get the outputs for decision making. That is the region proximity attribute based query or the statistical analytical insight in the development simulations. I would quickly come to the applications. So I have demonstrated out of many applications which are possible, because the main work is to convert point cloud to analysis ready point cloud that can be used for many applications. So here I have represented a few. One is for urban governance, highlight the buildings in the given spatial extent. Then another one is related to the urban greens. Urban green, everybody is talking about the problem. And here is the solution. With LiDAR data, we are already having the vector maps. With LiDAR data, I'm able to count the trees. And with the length of the road, I'm able to tell, like, in this road, these many trees, or in this patch, these many trees are possible. So with the gap analysis and priority-based forestation drive can be done at the decision making. This is I have shown for one road, but this is an algorithm. It can be done for all the roads, and we can give the ranking to the roads that these roads should be, like, on base of gap and priority base, it can be done. The other application demonstrated here is of asset management, power line asset management, information extraction. This is one of the class from the Dales data set. We have where we have got the point cloud data. So as the output, if I'm outputting, like, in this particular ward or administrative location, how many power lines are eligible are there? Or if I'm putting, like, I want to construct a house there, which is the nearest power line, and what are power lines are there, with what that information also we can get as metadata, as 3D output, as object, and also as a point cloud. Another application that we have is of disaster mitigation. This is over the Trivandrum data set. Here we are displaying the houses which are in the flood zone within a given ward. So when we are talking at the administrative level, we are not talking about the complete city. So in that ward, if you can see, like, we are getting the information, the latitude and longitude of the houses which are in the flood zone, high risk flood zone. We are getting their point cloud data, so we know the shape, height, and other features. Here also we'll know the height, we'll know at what depth they are located. And here we are getting the building model of it, and this is just the zoomed in patch of that. So we are getting the count, the metadata, and other. So we again came to the performance evaluation as time efficiency, scalability, space efficiency, Sustainability, because over a period of time, we can add more objects, we can add more regions, and also we can use it for the more applications. Yes, 1 second. In the future work, we would like to optimize this pipeline and develop it further. Yes, to give a very good web-based visualization so that for each and every application they can use. We'll be dividing our applications into 3 domains: decision-making, then sustainable development, and governance. So as you can see, this is the one like simple web-based visualization over the Trivandrum data. These are the applications: mapping, monitoring, analysis. And in conclusion, the broader scope of this work is how the data-driven urban planning can be done so that fact-based empirical decision-making can be taken. And another pillar of community engagement, because as I showed you that small video over Trivandrum, similar to that, if we are able to show the insights on a web platform, community engagement can be done. Because we are, as a decision maker, can influence 10 people or make the policy which 100 people will follow. But when the community sees that, the impact would be more better, like if you want to improve the governance perspective. So in conclusion, the cities are growing and we have a great need for efficient governance, policy implementation, sustainable urban development. In this picture, 3D sensing over the urban landscape comes as a prominent role. And in this work, we used bimodular, ontologically based, object-based storage framework to convert our point cloud data to analysis point cloud data for sustainable smart city development. These are my publications. The information extraction framework was published in Journal of Spatial Sciences, and I also presented a small part of it, and now it is published in the ISPRS Archives of Photogrammetry, and one on the machine on the deep learning based point net and net is published in this conference. Thank you, and I'm open to questions and suggestions.
Or it's just for visualization? Because your topic is technological assistance.
Decision support system. Decision support system.
Have you planned?
Yes, yes. Like when we today see Bhuvan 3D, it is for 3D visualization. A lot of platforms are there when we see digital twin. It is only for visualization. But if you can just, in that visualization portal itself, if you can make a decision support system, that is what the main thing is. Yes, and that is where, like, a lot of applications I have shown. So in that decision support system, we'll be segregating like what type of decision related to the policy implementation, governance, because here we are making the data set of every object that is possible to extract from the point cloud data.
So in that portal, that query can also be.
Yes, 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 yes. It will be embedded in this. And that's what, like, information extraction. Mm-hmm. Mm-hmm. Mm-hmm.
The data extraction and other
Mm-hmm.
there will be no additional challenges.
Yes, yes.
Suppose you are going to do this particular thing and suggest you for decision support system, I want to do it. I have to do it for like smart cities means I should do it.
Sir, actually, when I talk about Trivandrum data, getting relevant insights only from the image is not very possible. As I showed on the web visualization also from the Microsoft Bing Imaginary, not all the houses are very prominently visible. That is why choosing LiDAR data was prominent here. If you talk about other states, for example, Nagpur, even with the raster, our bimodular framework can be efficiently done. That time we can take the raster image and do it the similar fashion. Information extraction, yes.
Try to demonstrate what is the accuracy associated with it, and then so that whatever your visualization tool which you should be very user friendly and
Yes,
somebody
yes.
can look at it.
Mm-hmm.
Suppose you are giving it as a thing. This way
So due to
use
scarcity of time, I couldn't make a video and show it
No,
here.
the
I
3D
do have.
3D visualization
Yes.
is quite good.
Yes, yes. 3D visualization
When
with
you are-
decision making.
You are interacting with let us say, the governors.
Yes, yes.
Want to give it to anybody
Mm-hmm.
who should use this particular thing. It
Mm-hmm.
should be user friendly.
Yes,
And
sir.
also it should, as Madam said, you should be able to query. it and all.
Actually, I have worked on this amenities planning under SysDP. So a lot of things there, we are working on different domains, socioeconomic domain. But with the remote sensing data and whatever data we are having, linking with that is like what?
There can
I
be
mean,
omission and commission error can be there.
yes, yes.
Those things you are not
Mhm.
touched up or have you?
No, I have not touched up due sparsity of time. Yes, because machine learning,
These are not
deep
able
learning,
to
yes. Yes.
broaden the scope of these things.
Yes, sir. Like the main thing is information extraction, which is like novel to my work. Otherwise, machine learning, other things are also like what we are doing research on.
Their data is
Mhm.
quite expensive.
Yes, sir. I was fortunate enough to get.
No,
Mhm.
somebody is not able to afford.
Yes, sir.
What is
Then
the alternate solution?
this bimodular storage framework can be applied on raster data. Mhm.
Expand the scope of the work beyond Trivandrum and try to. This is the takeaway.
Yes, sir. Yes, sir.
There's just a quick follow-up comment because nowadays LiDAR is becoming much cheaper. You can find UV
LiDAR is coming up as a new data.
Just one question, very quick one. How modular is your framework? For example, one particular area, a very tiny area of that wind cloud has been changed. What do you need to do in terms of updating that?
Yes, sir. Here we are storing our data as a metadata information and the point cloud storage. So if a new construction is done, change metadata. If point cloud is available, put it. If not, then at least the vector file along with dimension that also can be put, because we are showing the output as metadata, which is very prominent. Second, as a point cloud object model that I showed you for the floods object model. So even if it's, the vector file is the height, we can achieve that. And the third one is the point cloud. If we are having, it's good. Otherwise, we can artificially create if we are given with the shape and size architecturally CAD models. So that is the adaptability and scalability part of it.
Good afternoon, everyone. I'm Preeti Konkati. I'm from Center of Studies in Resources Engineering, IIT Bombay. I work with Dr. Karthikeyan Lanka on passive macro remote sensing of land surface variables towards assessment of soil moisture and vegetation dynamics. So in simple terms, soil moisture is the water content present in the soil, which is being measured in terms of volume or weight. And with the aid of within the electromagnetic spectrum, the low frequency passive microwave signals are sensitive to the water content present in the soil. So we use these radiometers, which measures the emissions emanating from the Earth's surface and to measure the soil moisture information. Over bare soil, it's clear the signal is coming from the soil, and these emissions are being affected by soil textural properties, soil roughness conditions, and in the presence of vegetation, they are being influenced by the overlaying vegetation. And with decrease in the frequency of these microwave signals, there is the penetration happening through the vegetation, and we could acquire the information of both soil moisture as well as vegetation properties. We model the emissions emanating from the soil and reaching sensor through physical model called radiative transfer models, where we model the emissions and their attenuations through the vegetation using this radiative transfer model. So here, the microwave emissions emanating from the surface, from the soil, as well as the upwelling emissions from the vegetation are being considered, and the downwelling emissions from the vegetation interacting with the soil and then reaching the sensor are being considered in this purpose. Within this radiative transfer models, we show vegetation in terms of vegetation optical depth as well as scattering albedo. So this vegetation optical depth is nothing but it shows the extension through the vegetation, and the scattering albedo talks about the volume scattering happening in the presence of vegetation. This vegetation water optical depth, which is being measured using this microwave signals, is important as it represents the vegetation water content through the over the vegetation. And this vegetation water content is indirectly related to the above ground biomass. So it has a lot of applications to understand the dynamics of above ground carbon as well as to know the tree mortality during droughts. I would like to mention, like with the aid of this low frequency passive macro remote sensing, we can measure the soil moisture as well as vegetation information in terms of vegetation optical depth at global scales and at a high revisit time of 1 to 3 days. So I would like to also mention that this soil water and vegetation water content in terms of VOD are intrinsically coupled. So it makes it complex to understand their interactions in the soil, plant, atmosphere continuum, and making it complex to understand the land atmospheric interactions. So with the interest of soil moisture and the importance of VOD, through my PhD thesis work, I focused on enhancing these retrievals using low frequency passive microradiometers. As the first part, I looked at the errors and uncertainties of these retrievals and then focused on novel retrieval algorithms to address the identified errors and uncertainties. And taking these inferences and retrievals forward, I also looked on the application part of the soil moisture and vegetation optical depth. I'd like to go to my first objective, that is addressing the errors and uncertainties of soil moisture and VOD retrievals from L-band SMAP radiometers. SMAP is a soil moisture active passive NASA radiometer which works at L-band frequency. So the major goal of this study is first to understand the tau omega model, which is like a traditional radiative transfer model. Radiative transfer is a physical model. So we want to understand if it can accommodate the multiple scattering phenomenon, which is predominant over dense vegetated regions. And then later, we also wanted to understand how the soil roughness, which is the H parameter within this radiative transfer model, and how the scattering, single scattering albedo affects the retrievals of soil moisture and VOD. And we also wanted to look at how can we characterize their error propagations to soil moisture and VOD. So this work we recently published in remote sensing of environment. Here, we first assume the source of errors to be from various RTMs and the model parameterizations. Here in RTMs, we considered 3 different RTMs. First one is the zeroth order, which is the traditional radiative transfer model being used. And next, we consider 2 different first order RTMs called two-stream emission model and first order RTM model by Feldman. So these 2 are first order models. That means they accommodate multiple scattering phenomenon, unlike the traditional tau omega model. So, and in case of model parameterizations, we consider 2 different parameters. One is surface roughness as well as single scattering albedo. These are the model inputs of the RTM. We considered them based on the sensitivity of the microwave emissions to these parameters. I would like to highlight, like, we considered the previous literature and then considered a specific range of these parameters to land cover specific, and then took a 5 equal intervals of these parameters to understand the source of error and uncertainty. So likewise, what we did is we used the brightness temperatures from SMAP and generated an ensemble of 75 retrievals at various land cover types. Here for this purpose, I choose 10 reference sites. These are the core validation sites where they have in situ soil moisture network and been highly validated in the previous studies. These are of various land cover types with varying vegetation densities. As shown here. And we wanted to test and address the errors and uncertainties of various land cover types. So here we generated the ensemble of time series of retrievals of soil moisture and VOD for all these 10 specific sites. And then later we evaluated their performance and then used them in a statistical model called ANOVA model. In that model, what we did is we used this ensemble and then understood how much error is been coming from each source, which we have mentioned. Like, say, I would like to explain for the one of the plot there. It's a walnut. If you can see on the top left, it's a walnut bull site. So there we could understand how much error is been coming from soil roughness, scattering albedo, RTMs, and how are the errors from their interactions, say like from soil roughness and scattering albedo interactions, and soil roughness and RTMs as well. And the dotted line around the plot represents their statistical significance. So likewise, we talked about error and uncertainty. So when we are talking about error, we use directly the ensemble of retrievals. When I'm talking about uncertainties, what I did is I took the ensembles and removed their and only used their anomalies by removing the bias from the retrievals, and then try to understand how are the errors and uncertainties in both soil moisture and VOD. So when I looked at the errors, I found like there is a predominant influence of scattering albedo followed by RTMs and their interactions. Whereas coming to the uncertainties, when I removed the long-term bias from the retrievals, I could see like soil moisture is being unaffected by varying whatever the RTMs and whatever the scattering albedo and surface roughness used in the retrievals. Whereas coming to the VOD, which represents the vegetation part in RTMs, so this VOD has been highly influenced by the scattering albedo followed by the RTM which we are using. So based on these conclusions, we made few recommendations for future developments in retrieval algorithms, that when we are focusing on retrieving VOD, we have to take care of how are the RTM functionings being used and like to accommodate the scattering phenomenon properly within the RTMs. So I would like to mention that taking this inferences forward, later stages, I developed a dynamic vegetation parameter retrieval algorithm using this map brightness temperatures. Here, as from my previous analysis, I found a higher uncertainty in the VOD from RTMs and scattering albedo. So we want to look at the limitations to overcome the limitations of the current traditional zeroth order model in the retrieval algorithm. And then we also wanted to overcome the assumptions of temporally constant parameterizations and followed by the representation of seasonality. So we used a first order model called two-stream model in this objective. And then here I want to show that how can the error propagate from scattering albedo to VOD retrievals. So first we used a temporally varying VOD and omega in an RTM. When I retrieve a temporally constant omega instead of dynamic, there is an error propagation from omega to VOD of 0.63. So we would like to address this by simultaneously retrieving the VOD dynamics and omega dynamics with a temporally constant surface roughness in this multi-temporal inversion algorithm. So this multi-temporal inversion algorithm helps in retrieving VOD, dynamically varying VOD and dynamically varying omega along with a temporally constant H. Here we introduced a regularization of this algorithm to reduce their dependencies. Taking this forward I would like to show the retrievals from this developed retrieval algorithm. Here, by using the regularization as well as retrieving the temporally varying omega along with VOD, we could achieve a nice noise. So we could achieve the retrievals to represent the dynamics of vegetation seasonality as shown here. And also, we could also show the interactions between the VOD and omega during the dry downs. When we evaluated their performance with respect to NDVA and DVA, as there is no directly validating parameters are available, so we found that the current proposed retrieval algorithm based retrievals are doing better than the previous existing radiative transfer model based retrieval algorithm, that is regularized dual channel algorithm. And as a third approach, where I used a novel method to retrieve this VOD from the map brightness temperatures. Here, the first one is to estimate a VOD, which is independent of RTMs and the parameterizations, as we saw higher error propagations from them. And also to use a VOD-X, which is a higher frequency compared to the L band, and use this information into the model. And if we want to see if we could improve the retrievals of VOD or not. And we also considered a lagged climatological information, which can help us to retrieve VOD better. So here in this method, we considered various vegetation climatology, hydrological variables along with the brightness temperatures from SMAP, and developed a random forest model to estimate VOD directly. And in the scheme 2, we estimated NDVI and then computed the VOD. And then later we validated them with respect to baseline products like Sachi AGB, Jedi Ferrous Canopy Height, and NDVI and LAI. So when we validated them, we found a comparative performance with the baseline retrieval algorithm-based VOD. And we also found an improvement in the VOD performance in terms of temporal correlations with respect to NDVI for scheme 2 than scheme 1. And when I look at the Shapley value, which talks about the importance of the predictors, I could see like from scheme 1, the brightness temperatures are dominantly influencing the retrieval algorithm, retrieving VOD. Whereas when I compute NDVI and then use it to estimate VOD, there I'm seeing the climatological information is being useful to enhance the performance of VOD. And as part of my Raman Chappak fellowship, I worked on global scale soil moisture and vegetation information retrieval from patchy microwave. Here I use SMOS-based brightness temperatures. The current SMOS retrieval algorithm has some problems, like they have non-zero VOD retrievals over bare soils, and then improving the dry bias of this. So to address these problems, I focused on developing a new method to where I could enhance the surface roughness to address these issues, over which we use bare soils and then retrieve soil roughness and then use them to extrapolate over vegetated regions. This information is further being used for soil moisture retrievals in the SMOS IC, which is a current robust retrieval algorithm. And then we validated their retrievals. We could improve their dry bias and also improve the correlation with respect to the baseline retrievals, as well as the AGB maps as shown here. And yeah, and as an application, I looked at utility. So we, in brief, I would just like to say that we looked at the utility of VOD to understand vegetation response to drought. So here we could identify the vegetation response in terms of L and X band to look at 2 different levels of vegetation. And we identified that the VOD L and VOD X showed a contrasting response as they correspond to leaf level and stem level of vegetation water content. And during droughts, we could see like there is a strong stomatal resistance property which has been shown through this VOD L and VOD X. And over the forested pixels in South Asia, due to the moderate drought conditions, the photosynthetic activity has been unaffected. And we would like to take this conclusions forward to understand vegetation resilience to droughts. That's it. These are few of my publications. I have 2 RSE papers and 1 manuscript which is under submission. And I have 6 conference papers from this work. Thank you.